This is a chapter on alternating current circuits. We're going to put resistors, capacitors, and inductors into the same circuit and see what happens. And you might say, why? And my answer is, so you can record and reproduce sound is one of the better reasons. There are several biomedical applications of this, most of them involving the term impedance, which we will introduce. So first, capacitors and capacitive reactance. But even before capacitors, we're going to do a concept that is essentially a review, but will set the stage for the concepts in this particular chapter. And understanding this concept is important in thinking about what happens with capacitors and inductors. And what this concept deals with is the very simple circuit of an AC source with a voltage that depends on time equals some peak voltage, V0, times sine of 2 pi ft, like we've talked about previously. So that's a voltage as a function of time. It oscillates between positive and negative, and shown here is that voltage with its peak being here at V0 and its lowest point being at minus V0. That's the voltage. We also talked about the current resulting in a circuit like this. The current looks just like the voltage, except that its peak is denoted I0. No big deal. And its valley, the lowest point that it goes, is denoted by minus I0. But the important feature of this current is that it reaches its peak at the same time that the voltage reaches the peak. And this is significant. It means that the current and the voltage are in phase with each other. They reach their peaks and their valleys at the same time. Here's where they reach their valleys. The time here is the same as the time there. All right, so what are we asked to do? State the current voltage phase difference. Define the current voltage constant of proportionality. Let's do these one at a time. First of all, what's the phase difference? Well, they're in phase, so the phase difference is 0. The current and voltage are in phase. So the phase difference is 0. That's the language that we use. All right, define the current voltage constant of proportionality. Let's do that part next. Here's the current, the RMS current, the root mean square current. Here's the root mean square voltage. How are they related to each other? Back in chapter 20, we talked about that you can write V equals IR, and then applied to an AC circuit, that same equation applies by replacing the V, which is a time-dependent quantity, and the I, which is a time-dependent quantity, with the root mean square voltage and the root mean square current. So that's back in chapter 20. It's just VRMS equals IRMS times R. It looks like Ohm's law, V equals IR. No big deal, except we're talking about root mean square values of these. So what is the constant of proportionality? Current voltage constant of proportionality. Well, what's a constant of proportionality between these two quantities? And you say, well, it's the resistance. And I say, yep, you're absolutely right. So the constant of proportionality is the resistance R. No big deal. Something we've done before. And then finally, discuss its frequency dependence. Now, this is important too. The frequency dependence of that constant of proportionality. What's the constant of proportionality? It's R. So there's the constant of proportionality. How does it depend on frequency? Here's R measured in ohms, and here's the frequency. Generally, it doesn't. It's just a constant value that doesn't care what the frequency is. That's what we mean by a resistor. So it does not depend on frequency. And okay, so there's this statement here, the same value at all frequencies. It doesn't depend on the frequency. Now finally, we're supposed to state the average power for an AC circuit. And this is, I've got this phrase right here, purely resistive, because we'll do two more concepts that are very similar to this one. And they'll look exactly identical. All these words will be the same except these last two words. Right now we're doing a purely resistive circuit. What does that mean? It means we have a source and a resistor, and that's it. We'll then extend these concepts to a purely capacitive, only a capacitor, and a purely inductive, meaning only an inductor. But now for purely resistive. What about the power? Well, the average power from this same concept, you can go back and look at this if you don't remember it, and we went through a fairly detailed argument to show that the average power, this P with the bar over the top means average power, was equal to the root mean square current multiplied by the root mean square voltage. So we get a power. And let me tell you, let me remind you of why we actually get a power. We got this from the general definition of a power, IV. So in general, for these circuits, I is a function of time. It depends on time. It goes positive, it goes negative, etc. V is also depends on time, and P might depend on time as well. That's why we're interested in the average of this, to average it over time. The reason we get an average in this case is that wherever the V, the voltage, is positive, current is also positive. Multiply those two numbers together and you get a positive number. Well, what about over here where the voltage is negative? Well, the current's negative too. And if you're multiplying the current by the voltage, a negative times a negative gives a positive. So you're going to get an average that, well, you're always going to get a positive number when you multiply these two time-dependent quantities together, and you'll get an average power out of the deal. Not so with capacitive and inductive circuits. All right, the graph shows the current as a function of time. For an electrical device plugged into an outlet with an RMS voltage of 120 volts. What's the resistance of the device? Well, we know that VRMS equals IRMS times R. V equals IR. We have VRMS. It's 120 volts. So that guy we have. We need IRMS. And what is it? Well, this is the current as a function of time. It goes from 0 up to 10 amps, then back to 0, and then down to negative 10 amps. So what would you call this current here? And I hope that your answer is that it's the peak current, I naught, is 10 amps. And I hope that you remember from chapter 20 that we talked about how to get the RMS current from the peak current. How are they related? You say factor of the square root of 2. Divide by the square root of 2. All right. The RMS current is will be less than the peak current. All right, happy day. Now, since we know I naught to be 10 amps, we can calculate IRMS, and we can now calculate the resistance of the device. To find the resistance, we'll just appeal to this equation, divide both sides by IRMS, and then substitute this relationship for IRMS into here. These IRMS's cancel. We get that the resistance is VRMS divided by IRMS, but IRMS is I naught over the square root of 2. And now we can just plug the numbers in. VRMS is 120 volts. I naught is 10 amps. We just read that value off of the graph times the square root of 2. Well, that'll give me 120 volts over 10 amps gives me 12 ohms times the square root of 2. And 12 times the square root of 2, the square root of 2 is about 1.414. 12 times square root of 2 is going to be around 17 ohms. And sure enough, if you plug it into your calculator, that's what you get. 23-2. State the current, voltage, phase difference, all those things that we had before for a circuit that is purely capacitive. All right, here's my circuit. I've got a capacitor and an AC source in this very simple circuit with a capacitor. Well, we're not in Kansas anymore. And the reason is the voltage and the current are no longer in phase. In fact, the current leads the voltage by 90 degrees. So their phase difference is 90 degrees. Now, we say that the current leads the voltage by 90 degrees. And let's take a look here and see if we can understand that. Here's the current. The red curve here represents the current, and the blue curve here represents the voltage. The time is shown on the horizontal axis here. So as you move in this direction along this axis, the time is getting longer, later and later and later. This is later and later times. So if you want to go to the earliest times, you're going to come back this way. And so the question is, which one of these reaches the peak at the earliest time? You say, well, here the current is at its peak, and it's at a peak at an earlier time than the voltage is. So that says that the current is leading the voltage. It reaches its peak at an earlier time than the voltage does. So current is leading voltage, and how do we know that it's 90 degrees? It's this amount of a cycle that we're talking about here. If we're talking about a sine wave, this is a quarter of a cycle to get up to the peak, then another quarter of the cycle get down here, another quarter cycle, and then another quarter cycle, 4 quarter cycles to make the entire period of motion. So this is 1/4 of a cycle. A cycle is 360 degrees, and so this is the 90-degree phase lag that we think about for, it's 1/4 of a period that the voltage lags behind the current. That's why we call this 90 degrees. All right. So that deals with the phase lag. What about everything else? Current leads the voltage by 90 degrees. The constant of proportionality between the voltage and the current is called the capacitive reactance, X sub C. So X sub C is the capacitive You see, I'm never going to be able to remember that. And I'm saying, yes, you are. No problem. This word looks a lot like resistance. So I think of it as a resistance. In fact, the capacitive reactance is measured in volts. I'm sorry, in ohms. It's like a resistance, measured in the same units as resistance is. And capacitive is an easy word to remember because you know you're talking about a capacitor. That's the only element that you have in the circuit. And it's given by 1/2 pi f, the frequency of this source here, how fast it's oscillating back and forth. That'd be 60 hertz for a regular AC circuit for your household, times the capacitance in the denominator. The average power is 0. You say, well, that's kind of an easy result. And I say, yeah, it is an easy result. It's awesome. How can you tell that that average power is going to be 0? Remember that the power is I times V, previous concept, and I and V are both depending on time. If you go over here and you say, in this region here, from here to here, what are the signs, meaning positive or negative, of the voltage and the current? You say, well, they're both positive. So if you take two positive numbers and multiply them, you're going to get a positive number. What about in this region here, from here to here? Well, the voltage, the blue line, is positive, and the current, the red line, is negative. So we're going to get negative power for this portion here. Well, what about for this portion from here to here? And you say, well, it's also going to be negative. Well, no, it's not going to be negative. Both of them are negative. Voltage and the current are both negative, and a negative times a negative equals a positive. So we're going to be positive here. And then what about the last little bit between here and here? Well, in this case, the current, the red one, is positive. The voltage is negative. It's below the axis. Negative times a positive is a negative. So what happens is that everything cancels out. The positives and the negatives cancel, and you get 0 average power. That's why we have 0 here. So the important message here is that a capacitor does not use up any power on average. A resistor does. All right, let's see if we've got everything. Voltage phase difference, define the current voltage constant of proportionality. What is that? The capacitive reactance, X sub C. That's a coefficient of proportionality. Discuss its frequency dependence. We haven't talked about that yet. So here's the capacitive reactance. How does it depend on frequency? Well, in the case of the resistor, it didn't depend on frequency, but this one does. And this capacitive reactance goes like 1 over the frequency. So as the frequency gets large, the capacitive reactance gets small. And if you plot the capacitive reactance as a function of frequency, then this is what you get. It's like 1 over, this is like y equals 1 over x from your mathematical studies. If the frequency is getting large out on this end of the tail of the curve, then the capacitive reactance is getting small. So this distance here is getting small. If the frequency gets small, so this is a low frequency, near 0, the capacitive reactance blows through the roof, actually, as the frequency goes to 0. And so this is going to be very important in our trying to understand and get a handle on how these circuits work, this frequency dependence of the capacitive reactance. Okay, an example. A capacitor in an AC circuit. So here's my purely capacitive circuit. Capacitance is 1.5 microfarads, and the RMS voltage is 25 volts. So what is the RMS current when the frequency is 100 hertz and when it's 5,000 hertz? We're going to need the capacitive reactance, X sub C. That's our first need. And that's 1 over 2 pi f times C. We're given, for part A, a frequency of 100 hertz and a capacitance of 1.5 microfarad. That's 5 times 10 to the minus 6. So we get a pretty good size capacitive reactance at that low frequency. So that means down here at 100 hertz, we get a fairly good sized capacitive reactance up here. Good size. What about 5,000 hertz? Let's do the same thing for 5,000. So I haven't drawn this actually to scale, but if we're out at 5,000 hertz here, then we can expect a smaller capacitive reactance, X sub C. And sure enough, we get a smaller one. We put in a bigger number for the frequency and the same for everything else, and we get a smaller capacitive reactance. Again, measured in ohms, same as resistances are. This number is smaller than that number. Perfect. All right, what about the RMS current? Well, the proportionality, and again, I think of these as V equals IR. I start with V equals IR. You've already learned that. You've used it in a lot of problems. So V equals IR. But what's the R in the purely capacitive circuit? It's X sub C. All right, but we're now interested in the RMS current. So I want to solve for this guy here by dividing both sides by X sub C. So IRMS is just VRMS over X sub C. So what this relationship says is that if X sub C is small, then IRMS is large. And here's the same equation. Here's VRMS, here's X sub C, and we get a small RMS current. If, on the other hand, X sub C is small, then we would expect a large current. They're inversely proportional. So we get a large current here. For a large frequency. And we get a small X sub C for a large frequency. All right, capacitor is connected to an alternating current power supply. So this is a purely capacitive circuit. If the capacitor is replaced with another one that has a larger capacitance, what is the effect on the RMS current and the capacitive reactance? Well, let's write down the equations. the capacitive reactance is 1 over, and I think you're getting it in your heads now, 2 pi F times C. That's the capacitive reactance. All right, and we also worked out what the current should be. Worked that out on the last slide. And now we're asked, what happens if we replace the capacitor with another that has a larger capacitance? Well, if you replace this C with a bigger number, and that will increase the denominator, which will make XC get smaller. So if C goes up, then X sub C is going to go down. You increase the denominator, you're going to decrease the result. Well, if X sub C goes down, you're going to decrease this denominator. It's going to get smaller. If you decrease the denominator, then you'll increase the number. And so IRMS is going to increase, get more current. And that's exactly what we saw for the case of different frequencies, but we're just considering it for the case of different capacitances. So which answer gives the right answer? RMS current certainly increases, and the capacitive reactance decreases. Yeah, that's our man.